Welcome to the podcast on sketching parabolas. Now, in our last unit, we looked at quadratic equations, and one of the things we looked at was how you solve a quadratic equation. We found a couple of ways. The first way was through something called the quadratic formula. I've listed the quadratic formula here. That is a formula that you are responsible for. You have to know what it is and how it is used. And that must be committed to memory. It will not be printed on the test. The second way we looked at solving quadratic functions actually came several units ago, and it came from, or quadratic equations I should say, and it came from changing quadratic equations into something called quadratic functions. To do that, we first got all the terms of our quadratic equation on one side with a zero on the other side. We then removed the zero and replaced it with a y. And y, we learned in our function notation, can also be called f of x. And once we got an equation in x and y, then solutions were ordered pairs x, y. And those ordered pairs could be graphed in an xy coordinate system. So the next step was to graph it, which we usually did with our grapher. So our grapher would come out and produce a nice graph for us. And then from the grapher, using the trace feature, in particular using second trace 5, we'd find our x-intercepts. Like this is a x-intercept -1, 0. This is the x-intercept 2, 0. And then we'd pull the x-coordinates off the x-intercepts to get our solutions x equals -1, x equals +2. And that worked for more than just quadratic functions. That worked for any type of functions. Now, quadratic functions are also what we call parabolas. Parabola is a nice cup-shaped figure like you see here. Notice the bottom does not come to a point. It's nice and rounded. If it opens downward, the top is nice and rounded. The sides of the parabola don't go straight up. They never go to a point at which they're going straight up. They're always going up and out. They're going up more than they are out, but both sides are going up and out all the time. Now a question arises. Suppose you didn't want such detailed information as the exact solutions. Suppose you were willing to take a real rough estimate of the solution. That's all you needed for what you were working on. Or maybe you weren't even interested in solutions. Maybe this was a graph of profit and you wanted to know at what value of x was profit maximum. Well, that would be right up here at the top. That would be maximum profit. And a rough sketch might get you close enough to maximum profit for your purposes. So the issue here in this podcast is there a way that we can look at the formula for a quadratic function or a parabola and just from that formula do a quick and dirty sketch of the parabola, which gives us its essential characteristics, whether it opens up or whether it opens down, tell us about the key features of the parabola. Now, before we can do these sketches, we need to know a couple of things about parabola. And the first thing is that parabolas have something called line symmetry. When we say a figure has line symmetry, what we're saying is there is a line associated with a figure called a symmetry line. I'll sketch that in here on our first parabola. And what we mean by a symmetry line is this. The figure, the right half of the figure, is a mirror image of the left half in the symmetry line. Or another way of thinking of that is if you fold on the symmetry line, the right half and the left half will be a perfect match. It doesn't matter whether it opens up or it opens down. Every parabola has a symmetry line. The point at which the symmetry line meets the parabola is a very important point on the parabola called the vertex of the parabola. And again, in this case, if I were to fold on the symmetry line, the right half would go over and fit right on the left half. The second thing we need to know about parabolas before we go to sketch them is that parabolas are dominated by their x terms. The essential characteristics, the characteristics of the parabola on a large scale. when the x's vary a lot, when the y's vary a lot. They are totally determined by the first term only. Notice in the two parabolas I've written here, the two quadratic functions, the second and the third terms are wildly different from each other. But the first terms are absolutely identical, negative 1/3 x squared. To show the dominance of that first term on a big scale, I'm going to actually graph these two parabolas on a graphing calculator. Here I bring up my graphing calculator. I turn it on, and you can see that I've already entered the two functions into the graphing calculator. I want to get a quick graph on a small scale, and I can do that, as you well know, by doing a zoom 6. So I do a zoom 6. And there's the first parabola being graphed. And whoa, is that the second parabola? It doesn't even look like a parabola. Yet there's only two things here, the two parabolas. So yep, that's the second parabola, but on a small scale. Now look at the window here. We're only going from negative 10 to 10 in the x and from negative 10 to 10 in the y. So from here to here is negative 10 to 10. From here up to here is negative 10 to 10, and on that very small scale, the two parabolas look the same. Well, I paused my recorder for a minute, and you can see that like magic the window has suddenly changed. Instead of going from negative 10 to 10 on both axes, it's now going from negative 100 to 100 on the x-axis. That's 10 times bigger in scale. And negative 1000 to 300, that's almost 100 times bigger in scale in the y-axis. And now take a look at the graph of the two parabolas, but first let me show you that I haven't changed the parabolas. The two parabolas are exactly the same as they were before. All I'm doing is changing the window to bigger numbers here in the window. So this is being done now on a larger scale, and I graph it. And here comes your first parabola. And here comes your second parabola, and they are clearly different, but now they both look like parabolas. Remember, in our original graph, one of them looked like a parabola that was over here, and the other one kind of looked like a straight line coming down through it. Well, that was on the small scale. On the bigger scale, they both look like parabolas, and they don't look all that different. Now, what happens if we go to even a bigger scale? Again, I'm going to change my window. Right now I start off negative 100 to 100. I'm going to pause and change the window. So I'm back again. Now instead of going from negative 100 to 100 in the x, I've gone even 10 times bigger than that to negative 1000 to 1000 in the x. In the y, I've gotten really big. Negative 100,000 to 30,000. Again, let me show you I have not changed the functions. The functions are still the exact same functions we started with, that on the little scale of 10 to 10 didn't look anything alike. Now look what they appear to be on the very huge scale. Here comes the first parabola. Here comes the second. You can tell that something's happening, and yet you cannot distinguish one parabola from the other. You can't tell which pixel goes to one parabola, which goes to the other. They have basically merged now into a single parabola. And that's what I mean when I say the first term totally dominates the parabola. Now the x squared part of the first terms are the same. So the part that's really affecting the shape of the parabola is this coefficient of the x squared term. And we're going to see its role as we proceed in our sketching. So let's talk now about how we sketch parabolas based on what we know. First off, if this coefficient a, the thing that multiplies x squared, is a positive number, your parabola will open up. That means it's going to look like that. If that first coefficient a is a negative number, it will do the opposite. It will open down. That's what happened in our parabola. The first coefficient, the number that multiplied the x squared, was negative, and when we graphed it, it opened down. These next two characteristics are not terribly important. One says if the absolute value of this is bigger than 1, like if this were a 2, I'd be doubling my x squared. In essence, making the parabola twice as tall. But you can't be twice as tall as infinity, and the parabola is infinitely tall. So this is kind of a much less important characteristic than the first two. Still, what we do is, instead of calling it tall, we call it narrow. We say that if the absolute value of a is, whoops, that shouldn't be 0 there, that should be a 1. If the absolute value of a is greater than 1, like a 2 or a 3, that's going to make it taller, which will make it appear to be narrower. And if the absolute value is less than 1, like a half, like we had here, it'll make it appear to be wider. So what are the actual steps now that we go through when we want to sketch a parabola quickly just based on its formula? Well, the first thing we're going to do is determine whether it opens up or down. We'll get a sense of narrow or wide. Again, that's not too important. The next thing we're going to do is something that's the easiest thing you can do with your parabola, and that's find the y-intercept. You do that by setting x to 0, so that's a real simple procedure. The next thing we're going to do is locate that all-important point called the vertex, the point where our symmetry line meets our parabola. We'll start off looking for the x of the vertex. For the vertex, I always designate a vertex this way. Since the vertex is a point xy, but a particular point xy, a point xy where the line of symmetry crosses the parabola, I give it the special name x vertex, y vertex. And so what I'm saying here is if you want to know the x value of the vertex, put negative b over 2a. That's a number that we're familiar with. When your parabola has only one intercept, that is when the square root part in the quadratic formula is 0, what's left is negative b over 2a. And that will give us the vertex of our parabola. And then if we want the x of the vertex, and then if you want the y of the vertex, just plug into the formula. Take f of x, put it in the formula, or take x vertex, put it in the formula for f of x, and that'll give you your y vertex. So let's try this. And most of the time, these first 4 steps are going to give you enough to graph your parabola. Once in a while, the y-intercept and the vertex will be so close together that you can't make a good drawing from those 2 points. Sometimes they'll actually be the same point. In that case, you're going to need more points, so you just grab any x you want to, plug it into the formula for the parabola, find the y for that point, and plot that on your graph. It's like making up a little table of values. Okay, let's do the first problem. It says sketch the graph of y, or f of x, is equal to negative 1/2 x squared plus 3x minus 2. Now, let's go to a, the thing that multiplies x squared. It is negative. That means our parabola is going to be a downward opening parabola. The number part of it is a half. That means relative to a standard parabola, it'll be wider. So we're looking for a wide downward opening parabola in general. Let's go on and do our computations. The first thing says determine the y-intercept. Okay, we've already said it's going to open down, it's going to be wide. We get our y-intercept by setting x to 0. I'm not going to work this out by hand. You should be able to do this in your head. If x is 0, 1/2 x squared is 0, and 3x is 0, so y is just equal to negative 2, and I'll mark that on my graph. Y is equal to negative 2 right here. And I'll mark this as 2 and 4. Negative 2, negative 4, 2 and 4. And I'll put a negative 4 here. Okay, so there's one point on the graph. The next point we need is the most crucial point in the graph. It's the vertex of the graph. The first step in getting the vertex of the graph is to find the x of the vertex, and that is going to be negative b. X vertex is going to be negative b over 2a. So we go to our equation. b is 3, a is negative a half. Don't forget the negative. b is 3, a is negative a half. So on the top we have negative 3. On the bottom we have 2 times negative a half, which is negative 1. So for the x vertex we get 3. Now what does that tell us? Well, remember that the line of symmetry goes through the vertex. So that's telling me the line of symmetry for my graph is right here at x equals 3. This is the line x equals 3. So my vertex is going to be somewhere on that line. But where on that line is it going to be? Well, that's the y of the vertex. Now, according to my rules, to get the y of the vertex, find f of x of the vertex. So I'm going to go f of empty hole is negative 1/2 empty hole squared plus 3 empty hole minus 2. And I got 3 for my x vertex, so I'm going to put 3's in the empty holes. So this first one is negative a half times 9. Half of 9 is 4.5, so that's going to be negative 4.5. Plus 3 times 3 plus 9 minus 2. Negative 4.5 and 9 is 4.5. Minus 2 is 2.5. So my y vertex is going to be at 2.5. Here's 2. Here's 2.5. So there's my vertex. 3, 2.5. Clearly now I can see that it does open downward because my vertex is above my y-intercept. My parabola has to turn right here and it has to go through this point. Now is where symmetry comes in. Since this is the symmetry line and since I have a point 3 units to the left of the symmetry line, that tells me there has to also be a point 3 units to the right of the symmetry line, and I'm going to get a really easy graph here for this parabola. Make sure it turns smoothly. Make sure it continues to go up and out. And there's my sketch of my parabola. My vertex is 3, 2.5. Highest point I reach on the graph is 2.5. Now let's try a graph where things don't work out so well. The next one says sketch the graph of what appears at first to be a much simpler parabola. Y equals x squared plus 2x minus 5. Again, the first thing I'd like to know is, does it open up or down, or is it wide or narrow? Well, this time the coefficient of x squared is 1 understood. It's invisible, but you have to know that there's a positive 1 there. And since a is greater than 0, it's positive 1, it opens up. So I know my parabola is basically supposed to look like that. If the points that I come up with don't give me this kind of a curve, I know I've done something wrong. Now a is not bigger than 1, or absolute value of a is neither bigger than 1 or smaller than 1, so this is neither wide nor narrow. That's not real important. Wide or narrow appearance really has as much to do just with the scale of your graph as it does to do with the multiplier of x squared. So I don't emphasize that one a whole lot. Next thing we'd like to know is our y-intercept. We'd like to know that because that's the easiest thing you can do. Again, to find the y-intercept, set x equal to 0. So y will be 0 plus 0 minus 5, which is negative 5. So I'll come down here 1, 2, 3, 4, 5, and there's my y-intercept plotted on my graph. The next thing I'd like to know is my vertex, so I start off with x vertex, and the x of my vertex is going to be given by negative b over 2a. In my quadratic function, my parabola, a is 1 and b is 2. So I get negative 2 over 2 times 1, which is 2, negative 2 over 2 is -1. Now, that means that the line x equals -1 is going to be the symmetry line for my parabola. So I've drawn it in here. That's the line x equals -1. Somewhere along this line is going to be the vertex of the parabola. Where on that line is it? And to do that, we need the y vertex, which is f of x vertex. So I write f with empty holes. So I write empty hole squared plus 2 empty hole minus 5. And since the x of the vertex was -1, that's what goes in my empty holes. So -1 squared is 1. 2 times -1 is -2. Minus 5 is -6. So my vertex is right here at -6. But what does my parabola look like? Well, I know from symmetry that since this point is 1 unit to the right of the line of symmetry, there has to be another point to the left. But what does the parabola look like? Does it look like this, coming way out to the side, or does it look more like this, coming up through here? You know, it's hard to tell right now, and the problem is that the points I have are just too close together to make a good graph. They're so close together that there's many ways I could draw that graph. So what I need is to find a point on the parabola not so close together. I could go for my x-intercepts. That would be easy if this would factor. In other words, to get my x-intercepts, I set y equals 0. So I'd have 0 equals x squared plus 2x minus 5. And if I could factor that, I could find my x-intercepts, but I don't know how to factor that. So how do I find another point on the parabola? Well, it's actually very easy. Just pick an x that's a unit or two over. Let's say I want to know what y is when x equals 2. I just pick x equals 2 and I plug it into f. F of empty hole is empty hole squared plus 2 empty hole minus 5. If I want to know f of 2, it's 2 squared plus 2 times 2 minus 5. So that's 4 plus 4 minus 5, which is 3. So if I go over here to x equals 2, I get y equal 3. Now, I can get another point from symmetry. If this point is 3 to the right of the axis of symmetry, then there has to be another point 3 to the left of that symmetry line, and now I can do an excellent parabola. By just going right through those points. So that's what you do when your y-intercept and your vertex are too close together. Just grab another x value, plug it in. That'll generate 2 more points on your parabola. You can complete your sketch, and that completes the podcasts on sketching parabolas.